Okay, we are back at it. I realized I had music going in the background, which is YouTube's like, that's copyright, and they cut my audio for that video that I made that I worked really hard on. Oh, weep. But I cut it off for this one, so we will see. Anyways, so I'm fairly certain where we left off is we calculated, get rid of this little thing I was doing here, calculated our arc length for this guy. Because again, for this third section, because it wants three things. It wants the X and Y coordinates for the missing values. It wants these, and I talked a little bit about how I wanted you to do that because you can run through those fairly quickly, and there's only so much space available. But then it wants the arc lengths, which are very important. So I know that arc length is equal to theta, so the angle in radians times radius. So we also talked about in the first video how we got that formula. So I know that the angle in radians is equal to the arc length divided by radius, and I can rework that to solve for arc length, which we will also call S. So I know that this guy right here, so I'm going to call this arc, that says arc 1 for r equals 10, just because it's a little condensed in there. So it is equal to, what did we say? 3.927. So you'll notice if this circle is cut into 16 even segments, what do you think this total arc length would be? So again, just to clarify, when we are looking now for the arc here for the second segment, where's my, I just start. So same thing, circle radius of 10. Got my first segment, which I know is 3.927. Now we'll do that for the second segment as well. However, you're not solving for this. We're not solving for this because I know that's 3.927 because these are cut into even pieces. So say you have a pizza cut into 16 even slices. The measure of the crust is the same if somehow the person is a god and sliced the pizza perfectly so that every slice perfectly equal. What I want to know is this, the measure of the arc of this segment. So from my origin point right here. So if this is equal to 3.927, what do you think this will be equal to? Well, it would be double, right? Because I have two of these values. So it would be 3.927 times 2. Clear that out. Times 2. 7.854. 7.854. So that is what you're going to put. Oops, wrong window. That is what you will point right here. So arc 2 for radius of 10 on the inner circle is equal to, what did we say that was? 7.854. So, excuse me. What you'll notice is that for each increase, so this is 3.927, 7.854. You'll add again to get this total value for our third arc, and then for our fourth. So you'll notice again, our values there's some sort of change as our radius increases by this consistent amount of 10. So before I kind of give you that little hint, let's solve for arc 1 with the radius of, let me clear this out. So now we're looking here, our arc for our second circle. So you will be able to very shortly reach a conclusion that'll allow you to kind of similarly be able to just plow through the rest of these. So, but just to keep it pushing, let's look at the arc 1 for the second circle with a radius of 20. So let me clear this out. Oh, whoops. Once again, new, goodbye. Okay. So again, I know that my arc, which is S, is equal to my angle in radians times my radius. So same process, only thing that changes is radius. So this tells me that my angle here in radians is pi over 8. Again, we calculated that was I think the second thing we did. We found your normal angle, and by dividing 360 by 16, because there's 16 segments, then we converted that to radians. So I know that that this arc is equal to pi over 8. Sorry, I don't know why I did that. Pi over 8 times my radius, which for the second circle is 20. So we will go, if you go into Desmos, which would be here, pi over 8 times 20. 7.839. So let's go over, sorry, get my tabs mixed up. So I know this, so arc 1 for r equals 20 is equal to, what do we get? 7.85, I'll round that to 4. 7.854. So what you may notice is that our arc is going to just about double each time. So in the same way that it's expanding up here, when we increase our radius by the same amount each time, it's just going to increase by that same amount. So just to prove that before you go in and finish the rest of these, because just like before, if I know that this is 7.85, blah, 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 I know that if I have 2 arcs, it's just 2 of these, so times 2. For my third arc, so measuring from here to here, it's just 3 of these. So you can answer all of these now. So that being said, let's also make a conclusion about this one. So one, I know I kind of erased it. Hopefully you have it down. I had, it was 3.927. So maybe slightly off depending on how I'm rounding, but you'll notice that these are about doubling this way as well. So you have what you need to do all of these. You should have your X and Y coordinates for the ones that are missing. You should have an idea of how to do our radius, our point in the form of radius, theta in radians, and then also how to find our arc lengths. Cool. So that is, there are a couple other things for us to go over, but then we can wrap this up. So let's keep it moving. So Javier's noticed that the further away from the central tower, the farther the stakes appear to be. He suggests they should add radial lines to the diagram at the angles of, and so obviously if they're saying angles, but giving us this, the angle is in radians, not degrees, but only locate stakes at these angles on the circle of radius 40. So that would be out here. So what he's mentioning is let's change up the number of segments, because what you're going to notice is that these degrees are going to be different. So how do we convert these from radians to degrees? Well, let me see how I want to explain this. So I'm going to just go ahead and introduce you the formula. So kind of similarly, like we are, if you've ever had to like convert currency. So let's say that, again, how often am I going to? Okay. Do not save. So let's say that you have 50 bucks USD. So let's say that I've gone in and I've introduced ADOC dollars. However, it's a tough economy. The value, the going rate of dollars to ADOC dollars is about $1 for every 2 ADOC dollars, so about half. So if you come to my country that I run and you bring 50 bucks, you're going to want to know, well, how much is that in ADOC dollars? Well, if the going rate is about $2 for every $1, it depends on which way you're converting, then I can multiply that by my 50. So I know that I have 100 ADOC dollars. Same thing. Say you are now going back to the booming capital of Ashburnham from my thriving metropolis. So you take your 100 ADOC dollars, the going rate from ADOC dollars to USD is $1 for every 2. So one USD for every 2 ADOC dollars. I promise this is going to be tied in a second. So if you want to find out what you're going to bring, you're going to multiply it by that. You're back to your 50 USD. So let's now apply that to what we are doing here. So I know that pi, one thing I think I said on Monday, 2 pi is equal to 360 degrees. It's the going, let's consider that our going exchange rate. So similarly, pi is equal to 180 degrees. So if I wanted to use that, it says here that let's create some angles on our circle where, what does they say? So the first one they give us is pi over 16. So what is this in degrees? Well, what we can do is we can go in and we can convert that. So this is my angle in radians. So what I'm going to do is I'm going to multiply that by my conversion ratio. And I know that it is 180 degrees per pi. Whereas, 2 pi is equal to 360. So if you go and you cross multiply, you will have pi, let's go like this, 180 pi over 16 pi. So these will cancel out. Pi divided by pi cancels out. And 180 divided by 16 will give us about 11.25. So every segment will be about 11.25 degrees apart. So we can also go and figure out, well, how many segments are there for this circle? If these are closer together, there's certainly going to be more segments. So if I know that each angle is 11.25 degrees, how can I find out how many angles there are that add up to 360? Well, you can go and do some division. I actually didn't plan this part out, so I have to do it. What was it? 11.25. So about 32 segments. Well, and I also could have used my brain and gone in and seen that that it's about half of 22.5. So it's double the segments. So anyway, so what do these angles measure in degrees? So pi over 16 is equal to 11.25. So I would like you guys to, if you can pause if you have time, try doing a calculation for one of these on your own. Try converting it on your own. You will notice that there will come a point where these are doubling, but get that practice in there. So Alice and Veronica love this idea of assigning him the job of posting all the stakes in the circle, since there will be twice as many of them. I guess they gave us that hint if we read ahead. He doesn't need to calculate the rectangular coordinates. He plans to just walk around the circle, which makes sense. I think what they're alluding to there is, imagine like you're using your angles to find where you're going to plot your stakes. So you know your coordinates, your x and y, like we found earlier. So I know I walk over this much and I walk here, plot my stake, go back to the middle, walk this much, walk up. If you know the arc length, you could just walk, 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 etc. So, okay, what's the question actually? One. Plans just walk around the circle. How far apart are the stakes on the 40-meter circle? Calculate this using Javier's method for problem 2. So let me real quick double check what his method for problem 2 actually was. Okay, so we're just going to use the formula like we have been doing. So in this case, we are going to use our new degrees in radians, which it actually tells us is pi over 16. And for this new circle, which isn't labeled there, this is beyond that. This circle has a radius of 40 with a total segments. Oh, geez, drawing with the mouse is tough. Segments of 32. So we could actually use, if I know there are 32 segments and I know that the circumference is 2 pi, we could do some work there. But let's do it, pretty sure. Let's do this the way that they requested, which is by using the formula. So I know that arc length, S, is equal to my angle in radians times radius. So we know these two things. I know that my angle in radians is the pi over 16 value. I know my radius in this case, like they explained, is 40. So if you go in, I know that my arc length is pi over 16 times 40. Do I have that down, or do I need to run into my calculator and do it? Okay, so if you go in your calculator, let's just double check this because I think practice is good. So pi over 16 times 40. Move over. 7.85, we'll round that to 4. Why am I going over there? Trying to upload these videos. 7.854. So that is the distance from each stake. So if imagine this is our circle. Whoa, it's not my best work, but imagine this is the circle, but it has 32 stakes. It's a lot. But so the distance from each one, there'd be more than these, is 7.8 blah blah blah, 7.8 blah blah blah. How do we calculate that? We use that formula that we came up with earlier. So now I think we are going to just get into defining some overall takeaways, and we will be done. And I will actually just go over one thing that I want you guys to try and do. I need to see how long these videos are going to total up to. I may just have you do the like takeaway questions at the end instead of having you guys do the exit ticket, and then I can check these when I come in, hopefully on Friday. Hopefully. So let's see. Okay, everything looks good. All right, let's clear this out. Keep it going. So being able to quickly convert between degree measurement and radian measurement will help Javier a lot. Develop a strategy where you can consistently convert angle measurements from degrees to radians. So I kind of referenced this earlier a little bit. So to get, I want to thin this a little bit. Does it have to be, I guess 1? What does that look like? I guess that's fine. So develop a strategy to convert from angles to degree measurement to radians. So how we can do that is you multiply the angle. Actually, I don't like how it writes here. I think it's more legible on the other ones. Let me switch. So from, it's a little better, degrees to, lock in a little bit, degrees to radians. Dot, dot, dot. So that's when you will multiply, what do I have down here? The angle measurement in degrees by pi over 80, or sorry, pi over 180, like we did in that example like 2 problems ago. Or you could do 2 pi over 360, because these are, again, I know that pi is equal to 180 degrees. I know 2 pi is equal to 360. These simplify to be the same thing. Like I can factor 2 out of 360 and cancel them out, and I get this. But so in case you ever see that, I want you to understand why. So what if we want to go from radians back to degrees? Well, think to my currency. My currency example is you just switch the process around. So multiply radian angle by 180 over pi. And you'll arrive at your answer just like we did in that example. Okay. So actually we do have one more. So these are answers to here and here. All right, I think this is here's our last actual math problem before I kind of go over one that I want you to do solo bolo. So Veronica has a very different proposal for the soon to be added, the much anticipated, everyone's excited for 50-meter circle. She wants to place a stake at every 15 degrees. Show how to calculate the arc length between stakes using 15 degrees in your computation. So let's think back to that formula I made. Well, rather, we made together because we're a group. So the arc length, or S, arc length, is equal to my degrees in radians, radians, times r, which is radius. So one thing to use this, because this question wants to know, calculate arc length. And it gives us 15 degrees. I need that in radians. So we just happen to coincidentally come up with a really nifty way to convert between the two. So let's turn 15 degrees into radians. So to do so, we will multiply 15 by, let me see, if we are going from degrees to radians, we will go pi over 180. So radians usually will have pi in their answer. So if we are converting from degrees to radians, a helpful way to remember that is pi will be in your numerator. If you're converting from radians to degrees, degrees will be in your end result will be in the numerator. So we will go over here. We are multiplying fractions. So remember, cross, not butterfly, whatever, cross multiply. So 15 pi over 180. So we need to factor this however we can. So let me see. Hold on, let's do this. So we want to simplify this is what I'm getting at. So 15 and 180. Can 180 be divided by 5? Yes, it absolutely can. 36. So if we were to go in and factor 5 from each of our answers, we will have 3 pi over 36. And this can be factored further because I'm fairly sure 36 can be divided by 3. Don't tell the other math teachers. Okay, so pi over 12. Boom. So now let's look here. Should I have gone the other way with you guys first? Sure. Oh, I see. Okay. So I apologize. So what we are doing here, I misunderstood the question. So it says, show how to calculate the arc length using 15 degrees in your computation. I thought that meant use 15 degrees to get into radians. If you flip over, you'll notice that on page 5, it says, show how to calculate arc length between stakes using radian measure. So what this really is, this is the answer to B. So this is the answer to B here. So we'll just keep going and finish this, and then we'll swap back. So I now know that my radian measure of degrees, so 15 degrees, is pi over 12. So I can go and use this now. So I know that my arc, my S, the arc that subtends the angle, is going to be equal to my degree in radians. What's my time at? Okay. Times my radius, which for the highly anticipated circle that everyone's super pumped about is 50. And we can just go like this. And if you go, we would want to go into our calculator and do this. So 50 pi divided by 12. Oops. So we will just round that to a nice convenient 13. You go 13.01, but you get the picture. So I will specify if I want you to go in and like calculate your answer, because I know sometimes I'm not always clear with when I want you to leave pi in, when I don't. So in this case, go in, I will say, give me your answer. If I ever say round to the nearest whatever, you'll know that you're calculating using a calculator. So what is our answer here? Let's just round that to 13. Keep it simple. 13 meters. So circling back to the question that I kind of messed up. So calculate the arc length using 15 degrees in the computation. So don't do not transform, translate, what word am I trying to think of? You guys get it. Leave it in degrees. Don't move it to radians. So let's go back here. Let's clear this out. So we are looking at 15. What happened to my, oh. We are looking at this with 15 degrees. So remember that we can set up a proportion, like a fraction of like how we used 15 degrees, or in the previous problem, I don't think it was 15 degrees, but we can find out how many slices there are in this circle based off this. If we divide 360 by 15 degrees, we'll find that out. So we're going to set up a proportion like we did in the very early on. So 15 degrees out of 360. And we can use that by multiplying, because this is like the slice. This is one slice, like 15 out of 360. And we will set that equal to, or I'm sorry, we're going to multiply that by, clear this out, use my eraser. So we are going to multiply this by our circumference. So circumference describes the whole way around. I'm going to multiply because I just want to know the arc of one of these stakes or one of these segments. So I will multiply that by my circumference, and if I am using 50 as my radius, I'll go 2 pi 50, and that will, I'll leave that like that, go over here, 15 over 360 times 100 pi. So this describes, this is my, again, circumference, describes the whole way around. In this case, this is 100 pi. That just looks like sticks, but this is bad. 100 pi, where my radius is 50. So, but with this part, then when I go and I multiply it by this fraction, this will tell me one of these segments, not the whole thing, just the measure of the segment arc. So if you were to go in, this would simplify to 1/24th. So we know there are 24 segments. Like if we went in and reduced this times 100 pi, what that really is we are really dividing by 24. So if we go in and do that, let me see. I'll just have you just go in your calculator. You should arrive at also 13 meters. Let's double check that. 1/24 times 100 pi. Boom. Nice. Math is so great. Okay. So these are both 13 meters. So how did we do this without converting to radians? Well, we essentially created a proportion. If I know that it's 15 degrees per segment out of 360, I know that'll reduce. It may not always reduce as cleanly, but to 1/24th. I know there are 24 segments. If we go in and multiply 15 by 24, get 360. I know the circumference all the way around when my radius is 50 is 100 pi. I want to know what the arc is for one of those, so I multiply it by 1/24th. I get this. Cool. All right, let's finish this up. I'm recording this the night before. I was getting stabbed all day, so really hope YouTube behaves and that these upload, and that I'm not just like, here's Delta Math. Anyways, so let me see. We are moving on to takeaways here. So what did I want you guys to write down for this? Skip that for now. We'll come back to that together. But this part. So takeaways. If a circle has been divided into some number equal arcs, then the angle measure of one arc is blank or blank rate. So what this is assuming, some number in degrees or a number in radians. So let's make that a little bit bigger. I want you to be able to see the question. So what this is going to say, so in degrees, where n is the number of equal arcs, So it was 16 for the first half of the lesson, then they flipped it around to kind of change the process. It's going to be, the measure will be 60 divided by n, where n is the number of arcs. So over here, what did I tell you guys that 360 was equal to? It's equal to 2 pi. Let me rewrite this. 2 pi divided by n, where n is the number of equal arcs. So I can find arc length for the angle of rotation measured in, let's see, degrees by using the formula. Actually, let me see. This might just be easier for you guys instead of trying to read my stuff. All right, behold the solutions. So if a circle is divided into n equal arcs, then the angle measure of one arc is 360 degrees divided by n, where n is the number of arcs, and so on. I can find the arc length for an angle of rotation measured in degrees by taking my circumference and multiplying it by a proportion, the fraction created by whatever the measure of one segment is divided by 360. So like before, in the last question we did, we were able to arrive at the fact that there are, what was it, 24 segments total? Right? Yep. So, and then we multiply that and we get just a fraction of the circumference instead of the whole thing. So I could find arc length for an angle of rotation measured in radians by using this formula, which is easier, much more simple. So you can see why radians in that case are fairly appealing. I could convert degree measurements to radians by multiplying the degree measure. So if I want to go from degree to radians, I multiply by pi over 180. Again, if our end goal, if I want to be in radians, then I should have pi in the numerator. If I want to get from radians to degrees, I should have the degree translation, the 180 in the numerator. So, cool. I hope that this has not been unbearable. You should be actually getting really close to the end of class. So all I want you to do, if you watch the whole thing, wouldn't blame me at all if you sped it up some, sped through some things. But I hope that I hope this was better than whatever you've been doing. I'm sure it actually has been pretty nice just chilling. But if you have a sub in there that wants to, hopefully you've just been watching this. So what I would like you guys to spend the rest of class doing, let me get that away because that actually has the solutions. You never saw that. Is do this. So we will do this together. Do this. So label each point on the circle provided with a measure of the angle of rotation in standard position, beginning with HA. Angle measures should be in radians. So what it wants you to do is come up with your arc measurement here in radians. So leave pi in your answer. So remember that this angle here is the same as this angle here. It's just larger, or rather, it just looks bigger. So clear that out. So what you can do, you can find the angle here in degrees based off the number of slices. You have plenty of different avenues available to you. So I will be probably just breezing through this lesson when I get back, but I will come and check to see who did this, because this will be very indicative of who watched my really amazing math video that I really hope can upload. So that's going to bring us to the end. I hope to see you guys on Friday. Thanks for tuning in my stream. Goodbye.